Our speaker tonight has a unique background. She's an engineer at Lexis Nexis Special Services. She develops large-scale supercomputing apps for government customers using HPCC architecture. Her first role at Lexis Nexis was all the way back in 1997. Please welcome Drea Leed.
It's really great to be here tonight, and it's really great to see such a big turnout. And because there's such a big turnout, I know that some of you guys didn't get the pamphlets and the feedback forms and the pens that I have up here. So anyone that would like one, please raise your hand, and I'll just pass them out before we get started. Feedback forms. Since I started work, I've worked with Java, .NET, PHP, a bit of C++, VB, a lot of enterprise architecture stuff. I've done Oracle database administration, SQL Server database administration, PHP, MySQL. And for the past few years, I've been working with HPCC and big data. And by big data, I mean we're talking about terabytes to petabytes worth of data, the kind of data that relational databases start having trouble handling. And what I use to do that, and what LexisNexis uses to do that, is something called HPCC. So it's an open source big data platform. And tonight I'm going to tell you a bit about it. I'm going to kind of give you some concrete examples of how it works and the kind of things that it can be used for. And then, of course, we're going to be open for questions. If anyone has particular questions about whether it can do X, whether it integrates with Y, pretty much anything, it'll be an open forum for that. So, well, what is HPCC? Let's see here. My air mouse. Okay. Well, it is short for High Performance Computing Cluster. Very clear, not very imaginative, but that's really what it is. It is a cluster of off-the-shelf hardware, basically networked together to function as one large machine, one large computing platform. And those here who are familiar with Hadoop and Hadoop-centric technologies are going to start seeing a lot of parallels between the Hadoop world and HPCC. When LexisNexis first started, I kind of like to move around. Is this okay? Can everyone hear me? Yeah, okay. When LexisNexis first started, it was one of the first providers of big data, public records data in a lot of different areas. It was public records, court records, journal documents, a lot of free text stuff. And remember, this was back, they started in the 1970s. And so, being one of the first companies to pioneer electronic access to data, they actually started running into some of the big data problems a bit earlier than the other companies that started conglomerating and working with big data. They started out with a mainframe solution. That didn't scale. So they moved on to a relational database model, which worked quite a while. But eventually that stopped scaling either. And that is when we started looking into our own big data solution. This is before Bigtable, before Hadoop. But due to the evolutionary nature of big data processing and the rules that apply across the board, the solutions ended up being quite similar in many ways. So a cluster, like I said, it's parallel data processing across a lot of nodes. The language used to program HPCC is called ECL, the Equally Imaginative Enterprise Control Language. And it is used to break the data manipulation across particular nodes, work on individual nodes, and then merge and work with data across nodes. I'm going to be talking in detail about ECL a bit farther on, because that's really how most people interact with HPCC. So we've been using it in-house for over a decade now, and it's been continually refined and improved. It was originally built to work against about 360 million public records that needed to be sorted, linked, and merged. And so it's actually a very mature language. It has a lot of features. It's kind of been through the ringer in-house, and LexisNexis decided to open source it in 2011 to make it available to the open source community. So what is it used for? Well, I mean, that's a pretty broad answer. It is currently used in a lot of different industry verticals, pretty much any place where big data needs to be processed. Well, entity linking and disambiguation is a big one. There are a lot of places where you might have several 100 million records that you want to disambiguate, cluster, and link. HPCC can handle that because it actually has a built-in linking technology, SALT, which was specifically built to manage to link all of the millions of public records that are, they're certainly not perfect. I mean, you all have had misspelled mail delivered to your house in the past, I'm sure. It also is designed to run very complex queries against both broad and deep data sets. Now, one problem you run into with big data is that you can usually run a query against a certain time frame of data, which is very broad, or you can run a query against a long period of time, but where the data set's kind of narrow. Mostly because to get the horsepower to run a query against very broad and very deep data, it's expensive, and there's not that many systems out there that can do it. Botnets are one example of this. HPCC is used to search across a month's worth of IP traffic for trillions and trillions of records to detect patterns which you wouldn't be able to see unless you had access to that whole month's worth of data across the entire data range. So it's also used for financial services. It's frequently used for fraud detection. If you have a case where you have social networks of people engaged in fraud, HPCC allows you to link particular people together and run complex algorithms against the data that you have. It's used for government. Government uses it for all sorts of stuff, mostly for analyzing flow of information. Healthcare. Right now, it's being used in healthcare to do parsing of free text medical records, to extract entities and information from them and create records from them that can be linked to other records, and then used to do things like identify drug interactions, patient histories, link together two records for two different people that you didn't think were the same patient, etc., etc. So it's also used in network security and other areas like that. Like I said, detection of botnets. It's really good for monitoring firewall logs. Anything where you have to monitor a lot of information and very quickly. Retail uses it quite frequently for capturing information about customers and for processing information like trying to reduce customer return, customer retention, what makes customers drop off, what makes them stay, etc., etc. And for telecommunications, there's one example where we have over billions and billions of call records that are being continually processed, collated, and analyzed. So as you can see, pretty much every industry vertical has a need for big data these days, and a lot of them are using HPCC, especially now that it's open source. So that's what it does. Now I'm going to talk about exactly what it is and kind of the nuts and bolts of HPCC, because I know that's what I like to see when I come to hear about a technology. As I mentioned, it is a high-performance computing cluster, and that cluster is made up of actually two different subclusters, you might call them. And the first one is the data refinery. The way the refinery is set up is you have a large number of nodes. You have one master node and 1 to 1,000 or more slave nodes. The master node coordinates the transfer of data and information between the nodes. The slave nodes do all of the local processing that they can and then hand data back up to the master node. This, to anyone that's worked with Hadoop, is very similar. It shares some similarities with MapReduce. And the data refinery is designed to crunch through huge amounts of data. There's usually about two to four processes running on it at most. And come up with pre-prepared indexes, queries, information like that. It's also used for ad hoc analysis. If you have a lot of data and you want to run some queries against it to see what's going on, you can run it against the data refinery with Thor. Now the other part of the cluster, which is actually fairly unique to HPCC, this is the data delivery engine. We call it Roxy internally. And this fulfills the role that relational databases play for some other large data platforms. The data delivery engine is designed to take indexed data and data sets and to run prepared queries against them, the equivalent of stored procedures, queries, that sort of thing, and return the data extremely fast. Unlike the refinery, which has one master node and a whole bunch of slave nodes, in the delivery engine, every node is both a master and a slave. The master receives a query, checks its top-level indexes, gets the data from the other nodes, and returns it. It's very fast. When optimized for simple index key seeks, when you have your memory settings correct, it can return, a single node can return up to 1,000 queries per second. Of course, that depends on the data you're talking about. So that's a pretty simple query, but it is very fast. So that is the hardware architecture. The way that people interact with it is by using ECL, the language I talked about, Enterprise Control Language. ECL is used both to write scripts that do ETL, cleaning, transforming of data in the refinery. It is the same language that is used to write queries and services and create the indexes that are going to be returned from the data delivery. It's I like it. It's a great language. It is in some ways similar to Pig. I'm not going to go into it too much in this slide because I will be talking about it in more detail in a little bit. And finally, the last major portion of an HPCC cluster is the ESP, the Enterprise Service Platform. Now this is the web front end for a cluster. Everything you want to do on a cluster, we have a web service for it. You can run ECL through the web service. It can be used to monitor system. It can be used for administration, to look at jobs that have run. Pretty much the entire system is set up with a web front end so that you can access anything that you want to access through a web service. Also, as part of this, as you'll see in a little bit, is a web GUI, which allows you to do a lot of this stuff through the web, as well as the ECL IDE, the ECL development environment. So it's what I'm going to do is, I'm going to talk about this cluster. By the way, this is all one package. You install HPCC and you get all of this. It's basically wrapped in a pretty box with a bow, ready to go. So what I'm going to do is I'm actually going to kind of step you through the process. Like, okay, this is HPCC, it's great. I want to do something with it. What do I do? Well, the first thing anybody that wanted to play around with HPCC would have to do is actually get themselves an instance of HPCC. Now, there's three major ways you can go about this. The first is you can download, I'm sorry, I missed that. Yeah, this is, for people familiar with the Hadoop world, this kind of shows you an equivalence between basically the two environments. The hardware can be the same. In fact, we frequently see Hadoop and HPCC running on the same hardware. Aside from resource contention, which would happen anywhere, they don't really conflict with each other. They can both run in parallel. So you can take advantage of both systems if you have them. The first option is you can download a local VM image of HPCC, and you can run it on your local machine. Now this is a fully fledged HPCC instance. It's a one-node instance, so if you're looking for supercomputing power, you're not going to get much. But it does let you play around with it. It lets you play around with ECL, with HPCC, see if it can do what you want it to do. It's great for development. Another option is if you want to see what a cluster actually runs as, we have an AWS Amazon one-click instance where you can, if you have an AWS account, you can log on. You can say, I want 4 Thor refinery nodes, I want 2 data delivery nodes, go. And you have yourself a cluster. You can connect to it, you can run against it. This is frequently where I've worked on a lot of projects that use this for proof of concept work, for development work, while the actual production cluster is being built. Now that cluster can be CentOS or Red Hat, Ubuntu. It runs off of commodity off-the-shelf hardware. So it's basically any box you have should work fine with it if it's a standard build. And for this, the installation instructions are available. It's fairly straightforward. If you're a Linux admin, you shouldn't have a problem with it. Even if you're not, with a little help from your friends, you should be able to get it up and running. So those are the three ways that most people worked with HPCC. So once you have your cluster, the next thing, obviously, that you have to do is load some data on it. So how do you do that with HPCC? Well, first of all, it takes the standard data types that you see in most databases: XML, CSV, limited data, flat data. You can also have binary data. You can have just large chunks of text. It handles all of those things. And then, when you load it up, the next thing you want to do is distribute it across the cluster. The way HPCC works is if you have a file with, say, 500 million records, once you load it to the landing zone, the next thing HPCC does is it distributes it across the file system. So if you have 10 nodes in your cluster, you would have, the same number of records on each node to start with. It would just distribute it record by record. One of the nice things about HPCC is you can redistribute the data later on the fly when you're processing if you want. We'll talk about that in a little bit. Another useful thing about HPCC is, by default, when you're spraying the data, it also automatically backs it up or sprays a backup copy. If you have a 10-node cluster, all of the data that goes on node 9 also goes onto a backup location in node 10. In fact, any data file which is saved to a cluster, by default, works this way. What this gives you is really great backup and restore capability. When you're working with large clusters, once you start getting into the hundreds of nodes or the thousands of nodes, we do have some 1,000+ node clusters at LexisNexis. Drive failure isn't just something that might happen, it is an inevitable weekly occurrence. And so HPCC, because all of the people that dealt with it got sick and tired of dealing with drive failures, was built to be very resilient. If a node goes down, the cluster itself will stay up, and it can actually automatically switch out a backup node with the existing node. So you don't lose any of your data, and then it can just continue processing. You can load this data through that web service interface I mentioned earlier. This is an example of that. You just say, I want to load a certain type of file. You give it the specs, you hit the button, and it sprays it to the cluster. You can also use the ECL language. And this is an example of what ECL looks like. See that standard file spray variable? That's using our file system library to spray data in ECL. This is used frequently when you have a batch process, say, that's monitoring the system for files arriving in a certain folder. When a file arrives, the ECL script fires off and loads it, and then continues processing the data. Finally, there's an external Unix DFU class, distributed file utility, which lets you do this from a Unix script, or Linux if you're dealing with it from there. So that is how you get the data in there. And then the next question is, well, how do you do things with it? And this is where ECL comes into play. Now, ECL was designed from the very beginning to work against a parallel cluster. It was written by people that worked on Borland compiler, and starting in 1999, they began working on this language where what you write is basically what you want the data to look like at the end, not how it's going to get there. It's declarative. That means that you don't have variables. You don't, say, okay, this is the data set, and I'm going to change this variable to be something else. It's basically a one-time thing. Say, that's my data set. That new one is my sorted data set. That new one is the top end of my sorted data set. And due to the structure, this lets it run in parallel across all the nodes. So as Eric mentioned, it does compile down to C++. And as part of that compilation, a whole bunch of optimization is done, which means it runs very fast. And it's really easy to write one line of code that will basically do what you need it to do. I'll give you some examples in a little bit. So, let's see. I think, yeah, okay. Here's where things are going to get interesting. So I thought you guys don't want to spend an hour scanning in PowerPoint, so I was going to actually show you a live demo of what I'm talking about in ECL, so you can see some of the power of IDE. However, anyone that's worked with PowerPoint knows that this can be a somewhat dodgy idea. Okay, here we go. So, what you're looking at right here is one of the things that I love the most about HPCC. It's the ECL IDE. It's a development environment for ECL. It's very much like SQL Workbench for people that have worked with that. And it's designed to let you code ECL, to do syntax checks, to run it, to look at the result, and then to make changes as easily as possible. So you don't have to code something, compile it, run it, go back and check something else. It's kind of all in one place. So if I was going to start here at the beginning, this is how you define data sets. You can see that the ECL IDE has some basic formatting to make it easier for you to tell what's going on. It also has basic syntax checking. So if something happens, you can double click it and it will tell you what's going on there. It has other useful features that a lot of programming languages enjoy, like autocomplete. So you can things like that. And it also allows you to run simply by submitting, and you click, and it runs, and then it completes. And you can look at the results, any results right there. If you want to change something, you can go back to the builder, you can rerun it, you can re-examine it. So it does take a lot of the pain out of programming for big data, at least compared to some of the other systems that I've worked with. You can define attributes, which you can reuse. For instance, this here is an attribute. This is a data set, and now any other piece of ECL can use the original person, and then any other piece of ECL can use that. So a lot of what you see in LexisNexis and other systems that use HPCC is people create attributes, and then they start plugging them into each other, building on top of them. So it's kind of a code once. You don't have to recode the same thing. You can use people's various attributes and let's go through them. Now, this isn't going to be an ECL tutorial. It's a big language. It's complex. It has a lot of stuff in it. What I'm going to do is I'm just going to show you 3 or 4 of the things which, to me, make it one of the more enjoyable big data languages to work with. So if we take a look here, here's an example of grouping the data, right? I'm saying here's that person data we were looking at. I want these 3 fields, and I want this sum field. And then what you see here, this persist, what that does is when you run this ECL, the first time it runs, it's going to create a temporary file on the server. The next time you run it, if anything in the script above this point has changed, it will recreate it. If nothing has changed, it uses that persist. Now, working with big data, even if you have a very large cluster, there are some jobs that take a lot of time. This makes it much easier. If you have 5 or 6 persist points along the way, you can just run it, change something, and you won't have to rerun everything from scratch. That's nice. We can submit this. You can also do create different named outputs. Filters are useful. What this is a list of all the names in that data set that are the longest length of the name. And you can basically do that in one line and come up with the output. So this is addresses with more than one person at them, and this is the longest names in the system. Now, as I mentioned before, you can look at this using more than the ECL IDE. This is that interface I was talking about. Everything that you run in the ECL IDE, you can also look at here. And you can get to this from anywhere that your network allows, really. So you can look at the results. You can look at the graphs. You can look at timings, the original files. If you want to see the files that they came from, et cetera, et cetera. So just two more things I'm going to show you before we go back to the fabulous PowerPoint slide. And both of these things are things which make ECL much easier to use in the long run, because the first is the ability to use functions for different data sets. Now, I don't know how many of you people have worked with big data, but a lot of times, if you have code, it's basically designed to work with a certain data set. And if you have a data set with different field names, different field lengths, different field format, you have to tweak it or come up with a separate version for it. ECL has something called a macro, where you basically say, okay, here's what I want to do. Here's the data set coming in, and this can be anything. It could be, it could have 10 fields, 2 fields, it could be anything. These are the names of the fields that I want to work with inside this function, and that is the function that you do. So you run this, and you can basically get the same process run against any data set you want. It's like most functions. Anyone that's worked in Java or, it's something you're used to, but in the big data world, it's a little more exciting. So say you're going to run against this. So here is the one data set. Here's the field added to that one data set. Here's second data set, very different. And you get that same field added to the second data set. The last thing I'm going to talk about is integration. Integration is key for pretty much anyone doing any kind of database work these days. And ECL integrates with a lot of different languages. It integrates with C++, Java, Python, R. There's other database integrations in the work. We're working on an RDBMS integration, and MySQL as well, and Oracle. Those are in the works. So we use this frequently when there's existing chunks of code. You don't want to have to rewrite them in ECL. You want to take advantage of what you have, right? So say you had natural language processing, the Stanford Natural Language Processing Java application. You wanted to take advantage of that without having to rewrite Stanford's fabulous suite of natural language processing algorithms in a brand new language. So to do that, I basically wrap this in the Java class. And here's the inputs. You define that external Java class, which lives on every node in the cluster. You basically deploy that Java plugin to every node in the cluster, and then you can run your data against it. And this is basically that function. Taking raw text and it's extracting entities, which look like that. So ECL really has nothing to do with this. All it's doing is handing something off on every node, letting it process and come back. And this is very useful if you have a process which takes a long time, which natural language processing does. It's one of the most resource-intensive processes out there. But now you can distribute it across a 100-node cluster and get it done in 1/100th of the time. That's kind of just a very kind of a brief whiz through ECL and some of the items. Of course, at the end during questions, if anyone has questions about whether or not HPCC can do this or want to know more, I'm happy to answer questions during the question period and also, of course, during the chatting afterwards. So aside from the IDE, which is great, makes it easy to work with, and things like integration and reuse of code, the other thing which makes ECL pretty spectacular is the optimization. Now, anyone that's worked with Pig, this is going to look pretty familiar to you because Pig is similar in many ways. You write a single line of code, and behind the scenes, it's parsed into MapReduce code. Here, ECL is similar. I would have to say it's a bit more full-fledged because it's been around for a long time and it has a lot of libraries that work with. It compiles down to C++. And a single line of code, it can break down to a lot of different actions. So let's take that first join up there. It's a pretty simple statement, right? I want this data set, I want that data set, I want to join on the ID and the parent ID. When you run that, it's not only compiled down to C++, but as part of the compiled code, it's going to redistribute distribute that data set by default by that ID across the nodes. And it's going to redistribute the other data set by the parent ID across the nodes, and then do a local join, and then do a whole roller join. Just by default, that's what it does. Now you can give it hints. You can say in the second join there, well, you know, this write data set is really only a set of 200 IDs, so load that thing into memory. And in that case, you just load the right-hand side into memory and do the join. You can also, if you're a bit of a code control freak, control it completely. You can say, well, that's nice, but I want to distribute it in my way. You can say, I want to redistribute this data set by these two fields, redistribute this data set by these two fields, and then do a local join. So from kind of just no-brainer, let HPCC do it, to very explicit control of exactly how HPCC does something, you have your pick of what you can do. And this holds true for most of the primitive functions that you have in HPCC. So yeah, this is kind of another example. First, it's just a sort. Second is a local sort. Third, if you want to do a radix sort, you can basically distribute it based on an algorithm and then just do a local. And this is what they ran against the Hadoop parasort benchmark. And it did perform, it performed better. I don't have the stats, but it performed better than Hadoop doing the same work on the same kind of data. Another thing the ECL does, which is pretty slick, is if an attribute has been defined and another attribute is defined as that same thing, it basically stores the first one in memory and retrieves it. So that you have, it basically simplifies the code. It also, if there's ECL that's not being used, it's not going to get compiled. Because ECL, it kind of compiles from the bottom up. First thing it says is, okay, I'm going to output this value. What is that value? Well, that value is this value plus 20. What's that value? That value is 1. This never really even gets compiled, which makes things run faster. Sometimes, in some cases, you have code that's going to run. Other cases, you don't. And in this case, you don't have to worry about that. So that is basically ECL. The other item I'm going to focus on is the data delivery engine. I know I talked about it briefly beforehand, but I know you guys are primarily database people, am I right? So you're going to be interested in the delivery engine, Roxy, which functions, for all intents and purposes, as HPCC's back-end database to deliver queries. So the way it works is you have, say, 10 nodes in a Roxy cluster. You will send in requests to each node, and that node will process the request, consult its indexes, which I'm going to talk about in just a sec, determine the location of the data itself, what slave it lives on, and pass the request over to the slave. Slave listens for incoming requests. Once it gets one, it says, hey, I got this, don't worry about it, I'll deal with it. It returns the data back to the master, and the server master collates it and sends it back to the requesting process. So I mentioned something there called indexes. Yeah. Sorry, I didn't have the pretty picture. So let's talk about indexes. So I'll show you an index. When you want to work with HPCC and you want to create a query that people can access based on your data, you can take a data set, write a query against it, and deploy that out to Roxy. That's fine. But if you really want performance, what we do is we create an index against the data. This is how you do it. Here's a data set, and whoa. Now there are two kinds of indexes we use. First is fairly standard index. You have the key fields, and you have a file pointer to the record in the original data set that index record points to. That's very useful if you have one data set and you want to create multiple indexes against it. We also have something called a payload index. That is a set of key fields and a set of payload fields which are returned along with the keys. Now, it takes more room, obviously, than a simple key index, but it also means less disk access, so frequently it will perform better. It's kind of a trade-off between performance and disk space. And here you have an example of a payload index. All you do is you take the data set, here's the key fields, Here's the other fields I want to return. And then this is the file that it's going to be saved as. If you want to get data from those indexes, you can build it here. And you treat it kind of just like a data set. You put the filter in here. I want this data set where the zip code is this and the last name is like this. Or I want this data set where the zip code is this. And you can use a wide variety of functions and libraries that we have. Which you can see here. A lot of extended libraries that you can use if you want this data. Then the pointer index, it's basically just going to fetch data from this data set based on the file position pointer returned from here, using that field. So this is what you see. And it's pretty much the same kind of data. It's pretty quick. How this is used is you deploy this index to the data delivery engine. Say I just deployed this index here. And you can look at it in possibly see if it comes up. I'm running off my virtual machine right now. Anyway, you can access queries that have been deployed as a form, like you don't see here, as JSON or as XML through a web service. And in fact, inside ECL itself, you can connect with external web services and get data in. You can also, in addition to calling out to other web services, there's an ECL web service that lets you call ECL and get data back from that as well. Okay. The next thing I'm going to talk about is performance, because really that's the whole point of having the systems, is so we can perform better than your average bear. HPCC is a good example of adding more nodes. Basically, the performance levels out after a while. It doesn't. Yeah. The more nodes you add, the better the performance gets. Failover is very easily handled. It's easy to set up in the administration console. You can either have it automatically fail over to pre-designated nodes if the node dies, or you can basically switch it out, switch it in. With the delivery engine, because all of the data resides on multiple nodes, if a node goes down completely, the delivery engine keeps running. And it can run just fine, just a little bit slower until over half the nodes die, at which point it would close down. But that makes it very easy to have a 24-hour uptime for a delivery engine, Roxy. The easiest way to improve performance is really to scale out. With Roxy, in addition, if you set up a RAM disk or you preload queries into memory, you can get a rate of up to 1,000 queries per second per node, depending on the type of data you return. So you get some very good performance there. And that is really my tour of HPCC. Now, HPCC, it's a really big subject. There's a lot to talk about. So what I did is I kind of covered generalities. And what I'm interested in hearing is people's questions about it, because I know everyone has particular things they're interested in and particular areas that they are, would have questions about. So, yes?
Wait. Before we go on to Q&A, hang on. First thing, I want to give a great big round of applause to Drea Leed. And I want to remind everybody we do have a Kindle Fire HD to give away. All you have to do is put your business card or one of these flyers which are up here, so this will pass them around into this thing. Just pass these around, and if you haven't put it in, the bucket is going around. We will be doing the raffle shortly.
Linux-based. Okay, there are many ways you can schedule a job. One of the simplest is to have a cron job that calls the ECL plus command line tool to fire off an ECL script. A lot of people do that. ECL also has an internal alerting component where you can create a script that says, okay, I'm going to start you now, but I want you to wait until a certain event happens. This event can be a file landing on the file system. It can be any number of things. Once that happens, I want you to perform a certain task and then go back into wait mode. So from within ECL, without any other external components, you can do that sort of scheduling and monitoring. You can have it happen every half an hour. You can have it happen when something external appears. Yes?
So in your data store side, not the what I think you call Roxy, but what's called Thor,
Yes.
it seems like you've got two classes of nodes, the workers and the master index. I presume the master index is a single point of failure. If it goes down, is there redundancy built in?
For production systems, yes. You would always have a load balancer, and you'd always have a mirrored failover master node in place. The master node doesn't store any data. The master node, it contains the processes that communicate with the slave nodes and between the slave nodes. So if the master node goes down, your cluster will go down until your backup's in place, but the data itself isn't affected.
Next question?
Yes?
Given the ubiquitousness of Hadoop and Pig, etc., what's the value proposition going with some HPCC over using a Hadoop solution? Does it really scale to me to what their advantages would be?
Well, that is a very good question. I'll be honest with you, I have played around with Hadoop, but I have not built any production level systems with Hadoop. However, I've talked with Hadoop people, and the things which are the most useful to me is that really you get a lot of stuff right out of the box. You don't have to add on third-party components for a backend data store. The performance of ECL versus PIG, ECL performs better, although the syntax is equivalent in ease of use. And also ECL has a larger number of third-party libraries available. However, like Hadoop is it's open source. There's a lot of stuff that integrates with it. In a lot of ways, they're equivalent. I mean, it's really kind of a co-contested sort of question. HPCC is better with some stuff. Hadoop is better with other stuff if you want to integrate, perhaps using Storm, stuff like that. But yeah, in-house in LexisNexis, we did look at Hadoop for a little while. By the time we looked at it, we'd already built HPCC. And Google's big table came along, we're like, wow, we're kind of doing that. And Hadoop came along, like, yeah, we're kind of doing that already. So we did make it integratable with Hadoop. You can run it side by side if you have certain processes that you want to run in HPCC.
Questions from the other side?
Yes.
Did I say hand go up? Yeah.
How do you store internally? Sorry, how do you store internally data by columns, by rows? Any insights on those?
The data is stored primarily by row. It's basically distributed. By default, it's distributed by row. So one record will go on one node, one record will go on another node. You can specify that certain records go on certain nodes if you want to. Also, we can read HDFS data. The default format is a compressed, we call it 4 format. You can compress it. You can also encrypt it on disk, which is useful if you're working in certain environments where the data is very sensitive. It's always encrypted at rest.
I'm sorry, just to follow up with that. You compared for a moment Hadoop with HPCC. Have you compared it to any other database engines like maybe Vertica or Mongo?
No, actually we haven't compared with Mongo. I worked with Mongo on a recent project. It's really nice, but haven't done any actual benchmarking against other systems. We do know that a lot of cases where Oracle falls down, we Teradata, because we tried a lot of various RDB relational database systems and stuff like that before we went to HPCC. And for various reasons, HPCC was what we chose. Yes?
Is there any permissioning on top of data?
There is. We have permission and security at a number of levels. There's the encryption at rest that I spoke of earlier, where you have to have an encryption key available to connect with it. You can set up a cluster as HTTPS for basic HTTPS security. You can integrate with LDAP and other security and permission systems so that certain users that come in can see certain data sets and see certain queries, but they can't see other data sets and queries. And in some cases, like LexisNexis, encounters this a lot because we have some very sensitive personal data in our public records. People that come in from law enforcement, they're allowed to see certain things. People that come in from the credit side, they're allowed to see, maybe 8 out of 12 fields per person. Some people are allowed to see full social security numbers, some people aren't. So that's basically, it's another level on top where we keep a set of tables, a set of data files defining user permissions and incorporate those into queries to filter out particular columns that certain users aren't allowed to see.
That's column-wise. What about row-wise?
I'm sorry?
What about row-wise?
Role-based?
Row-based security. Horizontal security.
Yeah, yes, we have that as well. You can filter out certain rows based on if you have a key field that meets a certain format, you can filter that out up front. Yes.
How do you store the data? Do you have like distributed file system of some sort, replication, all of these things that kind of in Hadoop and
Yeah, we have a distributed file system. If, for instance, you had a 10-node cluster, the data is initially distributed across that cluster. As the data is worked with and changed and rewritten out, the distribution might change. But every time you write data to a cluster, it's also written to a backup location on another cluster, or
so
even
it's
two clusters.
one-to-one, or it's like there's like some factor of replication there?
It can, 1-to-1 is the default. You can have 1-to-2 if you have it. So it will back up.
So what happens, for example, if if it's one-to-one and something goes down, who will fail over? Who will restore whatever, let's say one node goes down, some of the data is just one copy right now. Who will do the duplication?
By default, it's replicated one time to another node.
No, I understand, but let's say one node went down. So the data that is replicated from this one node is just a quantity of one somewhere else.
Yes.
Who will replicate? So this node that went down is not going back up. So who will replicate?
There are two ways that this is done. The first is the manual way, where user comes in, says, oh, the node is down, pulls the node out, gets basically a new disk, puts it in, and then in the web interface that you saw, basically notifies, hey, this is a new node, replicate. And then HPCC replicates all the data from the backup directories to that node. That's common for development servers and things like that. For production servers, what you can do with HPCC is you can predefine a number of backup nodes so that they're in the cluster, they're simply not used. And you can set up HPCC and tell it, hey, look, if this node goes down, if you don't have any response from this node in a certain amount of time, starting with this backup node, basically you can switch it around, automatically replicate everything back to that node and use that as the existing node. Currently running jobs will fail and will have to be restarted, but you won't have any data corruption and the downtime is pretty minimal, about 10 to 30 seconds.
Can I comment on that?
Yeah.
I think it's quite inferior to, for example, to the way Hadoop does, which is always automatic, and there are more than two, usually 3 copies, and all these replications of the copies, which, for the node which is going down, happening behind the scenes.
Yeah.
So nobody needs to go to any interface and do something. I mean,
That's
the
the
users.
second method I talked about, the automatic method.
Right, but
And as
for
I
that.
said, by default, you
But-
can replicate once. You can configure it to replicate as many copies. You can have 3 or 4 different copies on different nodes as well.
But you said that for that thing to work, some node has to be put in backup mode, so they will not be used. So there will be a normal situation that will be just expense, because some nodes will be not used. In order
When you get-
to be backup copies.
You will, if you have a production cluster, you're going to get disk failure. That's just how it is, especially with large clusters.
That's
You
right.
need to invest in backup nodes, and you need to have those ready up front. You can either have them available, or you can configure them as part of the cluster, but you need to have them. So,
Okay, let's move on to the next question. Yes.
You were mentioning that when storing the data, we store it by key, and when we query the data, we query it by index, and it redistributes the data by index again, and then it brings it back, right? So my questions, I could be wrong with that understanding as well, please correct me. And what I was also going after is which one is impacting the payload, the index or the key?
Okay, what you're saying, I think you combined two things that I was talking about. Indexes, they're read-only, and you can read by keys and payloads once you create the index from the data set. Payload, of course, is going to be a lot slower because, you know, if you're just going to read a payload field, I mean, it's basically going to have to be a scan instead of just your basic C index. So for data sets, though, you can filter on any field, and that's usually done for the refinery when you're actually processing the data and preparing the indexes. Now, I'm not sure I answered your question. Could you repeat it for me?
Yeah, I was a bit confused on which impacts the payload, the time, as in does the structure of the payload XML change if I give a different index from the key that I use for storing? If my index does not match the key, like I give the key as ID, but I give my index as like year or date or something.
Oh, okay, I see what you mean.
Yeah.
And well, the payload indexes, since it's all basically one file, or well, equivalent to one file containing both the keys and the payload. If you decide that you want to skip keys, or if you want to use the second or third key, or if you just want to use the payload, it will do it, but you're going to have the expected performance impact. So that is the case. If you have the same data set that you want to query on multiple different keys and performance is very important, that's when you would have a non-payload index, where you would have individual indexes with certain sets of keys all referencing the same data set.
Okay, Drea will be here for one-on-one questions, so everyone will have a chance, but we only have time for one more QA question.
All right, so if you're loading data, you've got a big pile of data, you need to load it into your cluster. Is the cluster still available for other people to use to, query the data while this load process is happening?
Are you talking about the refinery where all the data crunching happens, or the delivery engine where you're giving a lot of queries?
I guess it betrays my lack of understanding, but
okay, well, if we're talking about the refinery, which is focused on crunching through the data rather than serving it up, you can be loading data, and that load happens in a different process than the process is used to run various work units. Usually, for performance's sake, we don't recommend more than 2 Thor queues on a refinery. You can have up to 4 if you have the resources for it, CPU-wise and disk-wise. But because you have a lot of processing going on, usually it's better to have 500 nodes with 2 processes running that can run really fast than 50 nodes with 4 processes running. Now, the data delivery engine isn't impacted at all by anything going on in the refinery. It copies a separate set of data sets to be available.
Okay, Drea will be here for one-on-one questions. Before we give away the Kindle Fire, I just want to give a great big round of applause. Thank you. Has everyone had a chance to put their card in to win the Kindle Fire? Going once, going twice. Oh, you got to write really quickly. And the pen's not working. This is the blank one. This won't be the blank. This will be the blank one? No, we need to have the blank. Did everybody else have a chance to put in the card while he's filling it out? No? Okay. Anybody left on that side? All right, we're waiting on you. I hope you win after all that. All right, then. It's under. Okay, can I ask you kindly to mix it all up? Mix it up good. Get the ones on the bottom. The people I do first need a chance to.
Put yours on top.
Put yours on top. Okay, now look in the other direction and grab one out.
He's fine.
And read it out.
Joan Angerman.
Joan Angerman? Engstrom? Does it say Engstrom? No, it says Engelman. Oh. That's you? Congratulations. Thank you all for coming. Drea is here for one-on-one questions. Feel free to come up and ask her right now. Thank you.